Hello and welcome to the Algorists. In this video, we will discuss how to implement iterative post-order traversal using just one stack. Please visit the chapter in the Algorists which explains how we can implement iterative post-order traversal using two stacks. And this is the follow-up discussion on that, where we will show how to optimize that even further, and we can do the iterative post-order traversal using just one stack. So let me show you how you can access the other um, chapter which shows the implementation using two stacks. So go to the algorists.com and then please go to the algorithms and the data structures. And here you see there is a series called iterative binary tree traversal, and there if you go to the third chapter, it says iterative post order traversal. You would see that it has the implementation which uses two stacks and does the post order traversal in iterative way. In this video we will discuss how we can do the same using just one stack. So let's start with a binary tree and see how the how the post order traversal works. As of now, I am taking a binary search tree, but it would work in any binary tree. So let's see how we can do the post order traversal using a stack. So we start from the root node. Let's take a stack here. And then we, as per the post order traversal, we first process the left subtree, then the right subtree, and then we visit and process the current node. So here we are what we will have to do. So the post order traversal for this one would be we'll have to go all the way to the left. So right now we are in 5. For 5 we will do the same post order traversal. We will see that the left node is null, so we will have to then process the right subtree. So we will come to the right node of 5 to, and so we will come to the node 8, and then we will again do the same thing. We will go all the way down to the left, and then we will process 7 because 7 has no left and right child. Then we will go back to its parent, which is 6. For 6 we will see that it has no right child, so we will visit 6. Then we'll go back to its parent, which is 8. We will process, so we just process the whole left subtree of the node with value 8, and now we will process its right subtree, and then we will visit and process the current node, which is node with value 8. So let's process its right subtree now. Its right subtree has only one node, so we process visit and process 9. Then we visit, so now we are back at this node at 8. We print 8. Now we are back to its parent node, which is 5, and we see that by now both the left and right subtree of 5 has been processed. So we visit and process 5, so we print 5. Now we are back to its parent, which is node 10. Its left subtree by now has already been processed. We just processed the left subtree. So when we come back here, we don't think about the left subtree at all. We check for the right subtree. We see that the right subtree is null, So we just visit and process it. We are back to its parent, like 20. We don't think about the left subtree at all right now, because we just processed the whole left subtree. So whenever we are back, we would know that the left subtree has been processed. So we move on to its right subtree, and we do the same procedure on the right child node. So we make this the current node, and we see that it has no left or right child, so we process it. And now we are back to the root, and we visit and process root with value 20. So if we have to do this using stack. Let's see how we can do it. By now we got an idea how it would work by using stack. So the first thing we did was we came down from the root, and the root is the current node. From the current node we came down all the way to the left. So let's put all the nodes on this path to the stack. So 20, 10, 5. So now like when I see that the left child is null, we make that the current node. So because we traverse all the way to the left until the current becomes null. So we were at 20. We saw we checked if it's left is null. So no, we made 10 the current. Then we saw if its left is null. So we saw no, it has a left node. So we made 5 the current. And then we made its left as current, and we checked if now the current is null. We saw yeah, the current is null, and we stopped there. We stopped putting the node values in the stack there. So and then we do a peek. We don't remove from the stack. We don't do a poll. We do a peek, and we check if 5 has a right node or not. If it has a right node, like we see that it has a right node, which is 8, then we would make current equal to the node with value 8, because we need to do the same process on this node now. And from there we again, if it has left child, we will go all the way down, putting all the nodes in the stack until we see the that the left child of a node is null. So we put 8, we go to its left, see that it is not null. We put 6, we go to its left, and it is 7, we see it's not null. Then we go to its left, and we see it is null, and we stop here. Now we do a peek again. We check, does it have a right node or not. We see it does not have a right node, so we pop it. So this is our expected, and we see that how the traversal result that we are getting, the actual one matches with the expected one or not. So we popped 7 because it has no right child, and we print it. Now we do a peek on the top. We see we have 6. Now we check, does this node has a right or not. We see no, it does not have a right child. So we poll that one as well, and we print it. Now we do a peek here. We are at 8. We see whether it has a right child or not. We see it has a right child. So whenever there is a right child, we make that the current node. If there is none, we don't change the current node. pointer, and the current node pointer will be null at all those time. So now the current node is 9. We check um, whether it has a left child or not, because if it has one, then we need to go all the way down the left path till we hit the null. We see, so we make this current, and from there we see if its left child is not null, but we see it is null. Then we check if its right child is not null or not. We see its right child is also null. So yeah, like when we are at 8, we had to put 9 on the stack, and since it has no left and right child, we also happen to first p like we picked the top of the stack. We got 9. It has no right child, so now we poll it. We remove it from the stack and we print it. Now we pick again and we see that we have 8. Its left and right child has been processed, and so we poll this node and we go back to 5. Its left and right child has been processed. We poll this node as well, and we print it. So I want you to notice a pattern here. When we find the left child is null at any point of time, we see if there is a path where that node is right child of any node or not. If it is, then we print the node, we go to its parent. So here 8 is parent, 9 is its right child. So when we are at 9, we saw that the right child is null. We immediately started checking, like I'm just thinking, I'm just asking you to notice this pattern, because this will be helpful while implementing. Like any pattern we notice, we like that helps in implementation. So like we just saw a pattern like here, and I will show you how that pattern has applied to 6 and 7 as well. So we were at 9 and we saw that the right child was null. We should check whether this node is a right child of another node or not. If it is, then we should process that node and we will move on to its parent node. We are at 8. We now check if 8 is right child of any node or not. We see, yeah, 8 is right child of 5. So we print 8 and we move on to 5. We see whether 5 is a right child of any node or not. We see no. 5 is left child of 10. It is not right child to any other node. So we visit and process, which means we print 5 and we stop checking for any other parent. I would show you. So anytime we see that the right child of a node is null, we should try to look for a chain like this, like a right path which has a chain of nodes. And if we find a chain, then we should print all the nodes in that path, starting from the leaf node all the way to the top of that right chain. I generally call this kind of nodes the root nodes, because they have subtrees or just one subtree rooted at them. So here I call 5, 8 are of type root. So let's see how the same concept applied to 6 and 7 as well. So when for 6 we saw that the right child was null, we actually did the same thing. We traversed all the way up till we get the current node as a right child of another node. So for 6 we saw that it is not right child of any other node, so we just processed it and terminated there and moved on to its parent. Same for 6. I mean same for 7. So 7 had right child as null. We under the hood we checked for if it is right child of any other node or not. We saw it's not, so we printed and we backtracked to its parent. So if 7 would have a parent to which it would have been a right child, then we would have traversed to that node as well and printed that node as well. So back to our traversal, we were at node 5, and now so 5 was yeah, 8 and 5 were removed from the stack when we were printing all the nodes in this path. And now we again peek at the stack, and we see that we have 10 on top of the stack. We check if it has a right node. We see it does not have a right node, so right node is null. So we do the same thing. We print 10 and we check if it has a parent to which it is a right node, and we see there is none because 10 is left child to 20. So we remove 10, we print it, and then we do another peek. We get 20. Its whole left subtree is processed by now, so we are not even checking anything about its left child. We go to its right, so the current node now becomes 21, and the whole process we did till now we will do on node 21. Now we will go all the way to its left side subtree till we hit null. So we see that it has no left child, so we check for its right child. We see that is null as well. Oh, and when we came to 21 from to 20, we pushed 21 in the stack, and then we peeked to check for left and right child node, and we saw both of them are null. So here also we are doing the same thing. After we checked the left child node and we saw that it is null, we checked if it has a right child. We saw that one is null as well, so we removed it from the stack, and we checked if it has a parent to which it is a to which it is a right child, and that is how we landed on the root at 20. So now since left and right subtrees are processed for 20, we remove 20 from the stack and we print it. We do this whole process till the time the stack is not empty. So right now, since the stack is empty, we know that the post-order traversal has ended, and we see that so let's try to check with the expected post-order traversal we have gotten before, and let's see if we got the correct result by doing the iterative post-order traversal. So we have 7. We have 7 followed by 6, followed by 9, then 8, then 5, then 10, then 21, and then 20. So we have gotten the correct result by doing this iterative post order traversal. We will next take a look at how we can implement this in code. So we will now write the code for the iterative post order traversal using just one stack. We will implement whatever we discussed. So we will be we are taking void because we will be just printing the nodes as we get. So let's define the class node. It will have one value. It will have left pointer and right pointer. For our convenience, I will just make it public as of now. Yeah, so definitely check for do a null check for the given node. So if it is null, we will just return, or we will do the whole processing if the root is not null. So I will take the current node and I will initialize that to the root, and we should do the processing till our stack becomes empty. So let's take a stack. I will take a DQ, which can be used as both stack and queue. So I'll just use it as a stack. New DQ. So this is the only stack we will be using in this code. And then while the stack is not empty, but if you see right now the stack is empty, so it won't even come inside the while loop. So we need to put one more condition here. The current node is not equal to null. So right now the current node is not equal to null because it is initialized to root, so it would come inside the loop. So the first thing we need to check is whether it has a left node. Check for, because in post order we first traverse the left subtree, then the right subtree, and then the node. So post order means left subtree followed by right subtree followed by current node. So left subtree of current node, right subtree of current node, and then the current node. So check for left child first. If not null, then put all the non-null children in the leftmost chain or path, whatever you say, in the stack, because that is how we do post order. We go all the way down in the left most path. So while current node is not null, we push the current node in the stack and then we move to its left child. So we will go on. So what this while loop does is it will go on putting the nodes in the stack until it really reaches a null node. So now all the we are all the way to the leftmost node. So what we need to check next is whether the node on which is on top of the stack, whether that has a right child or not. So node right, we at this point it is important to keep in mind that we should not pop the top node from the stack, because if this node has a right child, then we need to process the right subtree first, and after processing the right subtree we should pop this node from the stack and process it. So we won't do a pop, we would do a peek, and we would look for its right child. If the right child is not null, so it has a right subtree, and we need to do the whole process on the right subtree, treating the right child of the uh, on the topmost node on the stack as root. So so we are making this right child as the current node, and then it would go through this whole life cycle. Like it would actually then come here, it would look for the left child, and it would do the same thing that we are doing right now, treating the right child as the current node. But if it is not the right child, then as we discussed, we see, we definitely pop the top node from the stack and we process it, but along with that we also see if it is a right node of any other node or not. And if we find such node, if we see that it has a parent and it is its parent's right child, then we go on printing the parents as well, unless and until we see that we reached a parent which is a left child to its parent and not a right child. So let's take so let's pop from the stack and keep that in a node, and now I will check if it has any parent to which it is a right child or not. Very important to note here that this can be the root node of the entire tree as well, and if that is the case and we just popped it, that means the stack would be empty by now, and we are and then that would mean that we need to terminate here. So the first check that we need to do is check if the stack is empty or not. If it is not empty, then we would check if the stack.peak. So this is very important. If the stack would have been empty, then this peak call would have failed and would have thrown an exception here. So the first check that we need to do is whether the stack is empty or not. So here we check stack.peak.write equal to the node we just popped. So basically what we are checking is the node we just popped, whether that is a right child to its parent or not. If yes, then we process the node we just popped, node.val give some space here, and we assigned, so we stack the we pop the parent now from the stack, and then we assign that to node. So so like this loop will go on till we see that the node that we just popped happens to be right child of its parent. So the node on top of this path will be a node which is actually a left child to its parent. So at that time it won't come inside this loop, this while loop, and it won't print the value, but we need to print the value of the node which is the left child to its parent. So which means we need to do that here outside of the loop. This also applies to a node which has to a leaf node, where the right child is null and it is a left child to its parent. In that case, the control won't even come inside the loop, so we will be printing the value of that node here. Yeah, so this is basically it. This is the code of the iterative post-order traversal. um, so let's quickly see if we are getting the right result or not. So let's do a quick testing. I'm yeah here. So we need to change this class to be a static class, so so that we can use it in the static method. So I have the code ready for testing. This is, I just paste it here. So this is the tree on which I want to do the testing. This should be the expected answer for the post order. So and I'm calling the method that we just wrote here. So let's see if we get the correct answer. Let me run and let's see. Yeah, and bingo, we get the same result. We have the 40 followed by 90, followed by 45, followed by 20, followed by 30, followed by 10. So our test matched. Our actual answer is equal to the expected answer. Um, so guys, it was really great talking to you about the iterative post order traversal using the just one um, stack, and I'll be back with another video with some more interesting algorithms. Thank you and see you in our next video.